So I'm going to report on joint work with two colleagues. One is based in Chengdu in Sichuan, China, Binjiang, and the other one at Rutgers, Newark in the States. But before I do that, let me first make a disclaimer. I'm not going to talk about exactly solvable models because I'm not competent on the subject. Yet I have questions for you. Have you studied Phi 240? Have you studied Phi 420? Have you studied 516? So happy birthday. And I'm waiting for the answer. Yet a lot to do. So I'm going to talk about objects which we haven't mentioned here because they are, so you saw the title. Let me go back to the title. There are ugly words in it, meromorphic germs in several variables, and then we'll talk about a group. You can think of it as a kind of renormalization group. And why meromorphic germs in several variables? For us, it came from unexpectedly work on toric geometry by Nicole Berlin and Michel Verne, who were looking at the geometry of toric varieties. And for that, they needed to count integer points on cones. Now, you have to think of a cone not like an ice cream, but like a mathematical cone, an infinitely large object. And so counting integer points, so you put a lattice on your cone and you start counting your points, might take some time, and indeed you need to renormalize. And the fact that the cones might be slanted, not just quarter planes or eighth of a plane in 2 dimensions, but slanted in a let's say, comfortable way, this makes it trickier to renormalize the number of points. That was our original starting point, reading an article by Nicole Berlin and Michel Verne back in 2015, around 2015. I thought, well, they're renormalizing. And of course, they were not thinking of renormalization, but that was what they were doing. And they were using meromorphic germs in several variables. But since we're in a quantum field theory environment, let me start with, so this is, first of all, this is what I'm going to talk about. The main protagonist will indeed be meromorphic functions or germs. This will be to make sense of a multivariable minimal subtraction scheme. What does that mean? You have a meromorphic function in one variable. You write its Laurent expansion. You throw away all the polar part, keep the holomorphic part, evaluate it at 0 if that's where your pole is. That's the minimal subtraction scheme in one variable. We want to make sense of a similar concept in several variables. And then, having done that, we want to understand what we've done. We want to classify them and see how they relate. So I'll go back to some old work of the 60s, back to Eugen Speer, whom I asked recently what came out of his work at the time. He'd forgotten a bit about it, I think, and he told us that indeed it hadn't really been used by physicists, probably because it was very technical, involving meromorphic functions in several variables. So what does he do? He takes a Feynman graph and decorates each of the edges with a complex variable, let's say. So Zi for the ith edge. Usually what one does, thinking of dimensional regularization, one uses one regularizing parameter z for the whole diagram. In inserting this parameter z, or epsilon, whatever you want to call it, in the measure part of the integral. Here it's different. We have many of these parameters, one for each edge. There's an over-regularization scheme. We're regularizing too much, but that doesn't matter. We've got too many variables, but that doesn't matter. So that's what he does. And, and he says himself, in doing so, in introducing a regularizing parameter on each edge, he has functions of several complex variables. If he has k edges, he has k of these, each line of the Feynman diagram. And the main difficulty is the extension of Riet's treatment. Riet is just that, minimal subtraction scheme. You take a Laurent expansion, you cut off the polar part, keep the holomorphic part, and evaluate it at 0 if that's your polar. And he says, how do we do this with several variables? So that's the question we're asking. And what he does is that he shows, and it takes him some time, that the functions you come out with from a Feynman diagram are all of this form. Here it's a holomorphic function, a holomorphic germ. We're looking at the poles at 0. If they're elsewhere, we just shift them. So this is a holomorphic germ at 0. And these are linear functions. And you see the coefficients are 1 in front of the zi's. And there are different combinations of these zi's coming from the subdivergences. That's where the subdivergences are hit. So what do we have? We have an algebra of Feynman diagrams. Thank you very much. And then we're going to land in a certain set, algebra 2, of meromorphic germs, and they will all be at 0. This will mean that according to what we're going to start from, we might have different types of poles. This will stand for the type of pole we have. I'll do that because otherwise you'll be jumping up and down. So what are our protagonists? A, an algebra. We're going to equip it with the concatenation, very simple, just putting two Feynman graphs next to each other, or else two cones next to each other. Another source of inspiration for us are multi-zeta functions and their generalizations. And because a multi-zeta function is a sum, a discrete sum on a cone, so it's kind of related to integrals on cones. And so we can start with Feynman graphs. We can also start with rooted trees. From rooted trees, if we decorated the lines in the trees, we can also construct multiple sums or multiple integrals parameterized by these decorations on the lines. And this tree structure will also lead to linear poles. Or else, sums or integrals on cones. Either we want to look at the volume of a cone or the discrete volume of a cone. It doesn't matter so much where we come from for what we want to look at. What matters to us is where we land, here. It's an algebra of meromorphic germs with linear poles. The poles will be of different types, and what we will have, don't worry, don't bother to put the light on, don't bother because it's so short, is a map which will take us from this algebra, however complicated it is, of decorated objects with the zi's into meromorphic germs. What we claim is that we can forget this half, and as long as we know what kind of poles we have, we can work here and start from here. Now, what we want to do is spit out from these meromorphic germs some finite quantity. This is this idea of minimal subtraction scheme. Take out the poles and somehow retain from these meromorphic germs some finite information. So it will be an algebra, so there will be also a linear structure. But what's important to us is more this product. We're looking at a free algebra generated by these Feynman graphs. Yes, in that sense, yes. Well, if you decorate it, so that comes later. If you decorate them with independent parameters, with parameters that are not the same, and I'll come back to that later. So now we want to go to we want a number. So from here, we want to go to C, and that's where we're going to be working at this level. How to get a number from these meromorphic germs. And these will be what we call our evaluators. And what is important is that on concatenated objects, whether they're Feynman graphs, whether they're cones, or whether they're cones underlying multi-zeta functions, that we have a factorization property. This is reminiscent of locality in quantum field theory, but I won't talk much about this here. We'll just keep in mind that this is our guiding principle. We want this factorization property. And for this, we have to pay a price. The price we pay is that we, for each of these objects, we have a set of regularizing parameters, and here another set, and somehow they have to be kept independent of each other. This is what we're going to look at in the following. So what do they look like? Again, these meromorphic germs, holomorphic upstairs, and linear forms with some power. So according to where you come from, so that is what will kept the information about A will be kept on the type of pole. You will have, as Spear showed, sums of Z of the parameters. In fact, he shows that there's a nested structure, which we will use later on. You can have it more particular for multi-zeta functions. These subsets are very particular. They're really nested. So you take Z1, that's Z1 plus Z2, Z1 plus Z2 plus Z3, etc. In general, if you look at Laplace transforms on polyhedral cones, so this is Berlin and Verne, and we looked at that in detail, then you have a very big algebra which contains all the others. This is very general. You see, all we ask for is that the AJs are non-negative. And apart from that, you see this contains the other set, the other instances. So just as I was saying, Spear shows a little more than this. He shows that you have a nested structure in these linear forms that he comes across. We just want to remember from here that we have linear poles of a certain type. And the type is prescribed by where we come from. So how are we going to go about with a minimal subtraction scheme? So what do we want to do? We don't want to forget how we evaluated our pole is 0 here. we don't want to forget how we evaluate an ordinary holomorphic germ at 0. We just put 0, insert 0 inside, and evaluate. We want to keep that in mind, so we want to extend this linearly, but also multiplicatively in the sense that I described before. So what do we do for ordinary meromorphic germ at 0 in one variable? This is the polar part, up to -1 is the polar part, it comes here. And as from 0, it's the holomorphic part. So what do? We first project onto the holomorphic part, and then that's what we keep, taking out the polar part, and then evaluating this remaining part, the holomorphic part, at 0. And this is just the constant term at 0. Nothing much happens here. What does Speer advocate? He advocates an iteration of this procedure when he has several variables, Z1 to Zk. What does he do? He takes them one by one and evaluates, takes a minimal subtraction scheme in every variable one by one. And then symmetrizes in order to get something more symmetric, more covariant. It has the advantage that it indeed extends the ordinary evaluation. If we implement that on a holomorphic function in Z1, Zk, we're just evaluating. It doesn't matter what order we take, and since we're taking here a mean value, we get the ordinary evaluation. But if you do that, so you see, let's do that on this function. So let's take first the evaluation at Z1 equals 0 of f. What does that give you? Z1 equals 0, you get minus Z2 over Z2. And then you implement the evaluation Z2 equals 0 of this whole thing. Z2 equals 0. And what you get, -1. If you reverse the 2, because you've got a plus here, if you reverse the 2, you will get the opposite side. Z1 equals 0. Z2 equals 0. F, Z1, Z2. This will give +1. And if you take the mean value, you get 0. So it looks kind of arbitrary, because you could have stopped here, or you could have stopped there, or you could take the mean value. And of course, this is coordinate dependent. If you change your coordinates, then of course you expect a different expression, since this is very much coordinate invariant. So because of this coordinate dependent, I said invariant, I think I meant dependent. It's very much coordinate dependent. The only independence in the choice of coordinate is through this mean value over all the symmetrized expressions. So because it's, yes. So it is coordinate dependent, but there is one independence in the sense that it's independent of the order, because this expression is independent, it's symmetrized. So he's symmetrized in Z1, Zk. I know linear transformations, you'll get a different expression. So it is coordinate dependent. I think I said the opposite. So what we want to do is instead build a covariant way of evaluating using an inner product on the underlying space. The underlying space for a cone in dimension k would be Rk. For multi-zeta functions, there are also sums on cones, so it would be the space in which the cone is built. And for Feynman diagrams, it would be the space generated by the number, with the dimension given by the number of edges. So on this, having this inner product as a reference object, we will build what we call generalized evaluators following Spear. That's the terminology he used. And this way, we can build global multivariable minimal subtraction schemes. So what we want to do is the same idea as we did in one variable, namely, we want to first project so what we're going to do is first project onto a holomorphic part and then evaluate in an ordinary manner. There's no problem in evaluating once you're in a holomorphic part. The question is, how are we going to do that in several variables? And for that, we're going to use this inner product Q. So this idea of using an inner product came from reading the work of Berlin and Venn, who implicitly were using an inner product. So it came from the fact that they worked from a geometric point of view, they wanted something covariant. And then we want to classify to see how much freedom we have in choosing this projection and then evaluating. So that will be one way of doing it, but there are other ways. And in the last item, what we will do is relate any generalized evaluator to this scheme. So this we call the minimal subtraction scheme in several variables. This is a generalized evaluator. The idea is, how do these two relate? And this will be via this, what we call this Galois transformation. So again, there they are. And upstairs, I'm writing the holomorphic function in terms of linear forms instead of zi's, but that's the same. And what's important is that, so this is an example I gave here, and we're going to define the dependent set of one of these functions. It will be a vector space generated by these linear forms upstairs and these linear forms downstairs. Remember I said, how are we going to decorate our Feynman diagrams or our cones? We're going to decorate them for one cone next to the other. We're going to use one set of decorations, zi's, for one cone, and then another set. That's what Spear did. Here, what we're trying to do is define the dependent space in the set of parameters of each of these objects. So this function, the dependent space will be generated by the linear forms upstairs and the linear forms downstairs. And then we'll say that two functions are independent if their dependent spaces are orthogonal for this inner product that we've chosen. This will be the way of differentiating, of separating different objects with their decorations. The object with the decoration should have a dependent set orthogonal to the next object with its decoration. And we will call polar germs, you have to think those which are irreducible, those of the form H over G, which H having its dependent set orthogonal to G. So this, or to that of G. So this means that they're not reducible. You have to think of it like that. For example, if you take the canonical inner product, this is irreducible in inverted commas. This one is orthogonal to that one. This one is generated by E1 minus E2, and this one E1 plus E2, and they're orthogonal for the canonical inner product. Of course, they're not anymore for another inner product. So it depends on the inner product. But the advantage is that once the inner product is chosen, this is now coordinate independent. And what we use is that we have indeed an orthogonal decomposition of the algebra of meromorphic germs into a holomorphic part and a polar part. Those are the linear combinations of irreducible ones, okay? The ones that we're going to throw away, so those here, okay? With this one independent, the numerator independent of the denominator. And this is what we're going to throw away. So thanks to this direct decomposition, which is orthogonal for, so this means that anything here is independent from anything there. That's what we mean by this, this symbol up there, and it's a direct sum. In there, we have holomorphic germs, polar germs, and now we've got, thanks to this theorem, we've got the projection. So now we can indeed compose the evaluation with a projection. This gives us a global minimal subtraction scheme in several variables if we give ourselves the inner product Q. So this is it, evaluation at 0, composed with the orthogonal projection onto the holomorphic part. We call it EMS, minimal subtraction, governed by an inner product Q. And because this had this multiplicative property that I singled out at the beginning, when we combine it with this, we still have this multiplicative property. So this is retaining the locality property we had from whatever model we came from. So this is one family, one way of constructing generalized evaluators. Now, the question is, how do we relate any generalized evaluator to one of these? So that's where we stand. We have either Feynman graphs or multi-zeta functions or sums or integrals on cones. In fact, they're Laplace transforms of cones. They give us meromorphic germs at 0 in several variables. Now we forget this left part, concentrate on this part. What have we built? Thanks to this inner product on the underlying space, we've built a projection onto the holomorphic part, and which we combine with the evaluation to build a minimal subtraction scheme. When we combine it with the original phi, which took us from this algebra A to the algebra of meromorphic germs, we get a character on A, but it's a partial character because what we are asking is a product factorization property on objects which are decorated by z's, which give rise to functions which are independent in the sense that I gave above. So now we want to classify these evaluators. So we want to see how this relates to that. So For that, we consider maps on this algebra of meromorphic germs, which have the property that if f is independent of f prime, so this means that the decorations that gave rise to f have nothing to do with the decorations that gave rise to f prime. So this was this dependence space of f orthogonal to the dependent space of f prime, then this transformation should factorize. Okay, so it's all partial products we're looking at, okay, conditioned by this independence. The Galois group we're looking at, and we call it Galois group by analogy. Why? Because it acts on meromorphic germs, leaving holomorphic germs untouched. In fact, we ask for more than that. But to describe what we really ask for would require more technicalities. Namely, we define a notion of residue in several variables on these meromorphic germs and ask for T to leave the residue untouched, to stabilize the residue. So this is what to preserve the residue, which I don't want to talk about here. So in fact, we consider a smaller group than this one. And how does it act? So we have, in one variable, the minimal subtraction scheme, what does it do? It keeps the holomorphic part, throws out the polar part, and evaluates the holomorphic part at 0. Remember that from this decomposition theorem, we have that F can be written as a sum of a holomorphic germ and a polar germ. Now we're looking into this polar germ, into the dustbin, let's say, into what we're going to throw out. And this decomposition as a whole is unique. But what's inside this is not unique. It depends on what we choose as a family of poles. So let me just give you an example so that you see that the non-uniqueness, where the non-uniqueness can come from. So, for example, I hope this is correct. Otherwise, I'll leave it as an exercise to correct. So you see, we can have poles of this type, 1 over L, 1 L2, and then rewrite them as a sum. And this non-uniqueness is responsible for the non-uniqueness of the decomposition in this red part, so here. And here we're asking for so this is what we're going to throw away. It consists of holomorphic numerators and the pole part given by these 1 over products of linear forms we had before. So this is the S, consisting of these type of fractions. We're asking, as usual, because it's a polar part, that H be independent of S. So the numerator be independent of the denominator. Having done so, we can now understand how to act with an element of this Galois group on such a function. How do we do that? Remember that it preserves the holomorphic part, it keeps it untouched, and it's linear. And here we have again a holomorphic part, and this is there is a factorization here because this part is independent of that part. So this a priori complicated expression takes a very simple form, namely this one. So all we have to do is understand how T acts on the polar part. This is understandable for a renormalization type group. We want to see how it deals with what we're going to throw out, how much we're going to throw out. Okay, so on the polar part. And to a generalized evaluator, we can assign one of these. How do we do it? We just need to know how we, what we do with one of these polar fractions. We send S to S plus, and this is a number. This is the evaluator on S. It's a certain number. An evaluator is a linear map from M to C, which extends the ordinary evaluation on holomorphic germs. And this way, we can show the following theorem. Let me just recap all the ingredients that we've seen. And the splitting was an important ingredient. The projection was an important ingredient. The Galois group we've just seen. And what can we prove? That a generalized evaluator at 0, namely a linear form which extends the ordinary evaluation at 0 and factorizes on independent germs. This is this factorization property that we saw, is in fact modulo and transformation in this Galois group a minimal subtraction scheme. So they're all of this form. It looks rather huge, and it is quite big, but when you look at how it actually is built, this transformation, you see that it only acts on these linear forms. So for a set of linear forms, it's an automorphism group on an algebra, small algebra, built from these linear forms. You don't see all the holomorphic parts that are added onto here. I think I've got 5 more minutes. Yes? Okay. So, so that's the theorem. Now, how do we proceed for the proof? It might look a priori relatively simple because indeed this object is rather simple. But in order to prove this transitivity, it's in fact a transitivity of the action of the Galois group on meromorphic germs in several variables, we use Lyndon words for the shuffle algebra. But not usual Lyndon words. Remember that all along I insisted on the fact that you have that you work. Oh, let me just recap what this evaluator is. So what we've been classifying are objects of this form. So if you take 2 independent germs, the evaluator on the product is the product of the evaluators. So this relation on M endows M with what we call a locality structure. This is a binary symmetric relation on M. This is essential in order to keep the subdivergences separated. The whole idea behind these constructions is that we keep track of the level of subdivergences because each subdivergence comes with a different parameter. In order to do that, we need this locality structure. Now, we don't have algebras, we have locality algebras. What does that mean? That we have a partial product on these algebras. We only multiply when things are independent, when things are related by this binary symmetric relation. Having done that, we work with polynomial locality algebras, shuffle locality algebras, and Lyndon words for this locality structure. So we needed for that to reprove that Lyndon words, but in a locality setup, were in fact a basis for our locality shuffle algebra. Why do we have shuffle algebras? Because we have nested structures. I told you at the beginning that Speer identified the poles first in a rather rough manner for his meromorphic functions coming from for his meromorphic Feynman integrals. First of all, he had partial sums, and then later, in later work, he identified a nested structure. So when we look at chain cones, we also have a nested structure. And when we look at general cones, we can subdivide them into chain-type cones, which also have this nested structure. It's thanks to this nested structure that we find ourselves working with shuffle algebras. Shuffle, in fact, quasi-shuffle, because in a discrete setup, we have quasi-shuffle. So it's thanks to a transposition of the usual Lyndon word basis to the locality setup that we manage to prove this statement. Now, I thought until recently that meromorphic germs with linear pose was the most general type of pose you could come across from my experience. Feynman graphs, sums on cones, integrals on cones, multi-zeta functions, etc. But recently, we've added this character into our discrete sums. So these are generalizations of multiple zeta functions. This is a cone intersected with a lattice. These are linear functions. So this is more general than multi-zeta functions. And in a multi-zeta, when you generalize multi-zeta functions, you have a 1 here. Here we've replaced this by a character. This, with values in U1. This has the property that it leads to, so you have, you see you have the S here. These S's will lead to poles, which are not only linear, but which bring into the picture polylogarithmic type poles. So this is a new difficulty. We're struggling quite hard with this, and I wasn't expecting that until we dealt with cyclotomic conical Shintani zeta functions. You can just think cyclotomic multi-zeta functions. Now, I have an open question for Harald as a final comment to my talk, namely, are 80 years of life an exactly solvable model? Can you give us the recipe to keep such in such fit mind and state of health? We'd like to have the recipe for that. Thank you very much.